Hello everyone, my name is Xin Wang and this is the video presentation for image processing and computer vision project, and the topic is implementation and comparison of various noise filtering techniques. So first is the introduction, and I'm going to walk through the presentation in the following three steps. So the first one is the various noise types, next is the various filtering techniques, and the last one is implementation and comparison. So first, let's talk about the noise types. I'm going to use here are the four common noises that implemented in the image processing test. So there are Gaussian noise, Poisson noise, salt and pepper noise, and speckle noise. So Gaussian noise is its amplitude will satisfy a Gaussian distribution or a normal distribution, and Poisson noise is pretty much the same. It satisfies a Poisson distribution. And salt and pepper is interesting because there are bright noises on the dark background and also have dark noises on the bright background. And speckle noise is a kind of scaled uniform distribution noise. So next is the filtering techniques that I'm going to use in my project. So there are mean filter, median filter, Gaussian low-pass filter, Wiener filter, BM3D filter, and wavelet filter. So next, I'm going to introduce these 6 types of filters in detail. So first is the mean filter. It is also called the average filter, and it can be thought of as a convolution filter because every time you take a kernel and you do the convolution calculation with the original pixel values. So here, let's say we have a 3 times 3 kernel, and the ranges of the values of the pixels range from 1 to 9. And what mean filter does is it will replace each pixel value with the mean value of its neighbors. So the mean or average value in this kernel is 5, and it will replace each pixel values with 5 here, and do the same type of stuff for next kernel. And the next one is the median filter. It's pretty much the similar type to median filter because median filter replace the mean filter replace each pixel value with the mean value, but here the median one replace them with the median value. And usually the median filter have advantages over the mean one because the unrepresented pixels in the median filter won't affect the median values, pixel values, and the median filter won't create new unrealistic pixel values. It will just use the original pixels in the picture. Since, like, for example, we have a 3 times 3 kernel again, and the median filter, the median value of this pixels is 4, so we will replace all of the pixels in this 9 kernel with the 4. The next one is Gaussian low-pass filter. It's still a kind of convolution filter, but this time we will modify the pixel values with convolution by convolution with Gaussian functions. So for example, this time we have a 5 times 5 kernel, and when it's outer place, it's 1, it's the smallest value, and when it gets to the central part, well, it's 41, which is the biggest value here. It satisfies a Gaussian function, and Gaussian low-pass filter will remove high spatial frequency components from an image. And next one is the Wiener filter. The Wiener filter will provide a statistical estimate of an unknown signal by using a related signal as an input and filtering that known signal to produce the estimate as an output. And in Wiener filter, signal and additive noises are stationary linear stochastic processes, and this is optimal in terms of minimum mean square error, which means it will reduce the MSE value a lot. And also there are both inverse filtering part and noise smoothing part in the Wiener filter. Next one is the BM3D filter. It's a quite complex and advanced technology created by some researchers. It is kind of block matching and 3D filterings. Its concept is it will group similar to the image fragments into 3D data arrays, which they call groups. And by using collaborative filterings, the finest details will be shared by the group blocks and will preserve the essential unique features of each individual block. Here, the collaborative filtering is a special procedure developed to deal with these 3D filterings. It's a built-in function. And the last one is the wavelet filter, and we'll calculate the power spectrum by using wavelet transform, where the wavelet transform can be viewed as a high-pass filter, so you can use it to denoise. And also, wavelet filter contains numbers of filter banks to reduce noises, and also will preserve the phase, which is very important in image processing. So how do we detect the quality of the image? So usually we use MSE and PSNR values, and here I'm introducing a new type of parameter called structural similarity, which is also called SSIM, and here is the equation of it. And the usage of SSIM is designed to improve on traditional MSE and PSNR. It is a type of image quality parameter based on an initial uncompressed or distortion-free image as reference, and the resultant SSIM value is a decimal which between -1 to 1. So when you get to 1, it means that there are two identical images, and this time the SSIM is 1. When it's like 0.9 and it's approaching the 1, means the bigger this decimal value is, the better the quality is. So here I'm just use the traditional testing image, the Lena. This grayscale image is my testing image. So let's show a demo by using the MATLAB. So here's my MATLAB code. So first I read the grayscale image and implement 4 types of noises here: the Gaussian, the Poisson, the salt and pepper, and the speckle noise. And afterwards I denoise them. So the first one is Gaussian. So here I use FS Special for the average and the Gaussian filter, because there are types of convolution filter, and creates a 5 times 5 kernel here. So afterwards I use filter to do the average or the mean filter and the Gaussian low pass filter. And for the median and the Wiener filter, there are built-in functions already in the software, so I just use melt filter and Wiener to do the median filter and the Wiener filter. And here's the syntax for the BM3D filter and the wavelet filter. They are pretty much complex. And the same stuff for the Poisson, the salt and pepper, and speckle noise. And afterwards I output all of the resultant pictures into a folder that I created. I don't want to show all of the pictures at one time. It will be a total mess, so I just output them and store them. And afterwards I calculate the MSE, the PSNR, and the SSIM values for each denoising techniques on each kind of noise. So the first one is the MSE for Gaussian noise, the mean, the average, the Gaussian low pass, the median, the Wiener, the BM3D, and the wavelet. And also the PSNR values, and for the Poisson noise, for salt and pepper noise, for speckle noise. And also here is the SSIM parameter for Gaussian, for Poisson, for salt and pepper and speckle. And afterwards I combine them all of them into a single matrix. and display them to show which one has the best quality. So let's run this here. Since I'm using a remote controller, so it will take some time to run the code, but fortunately the grayscale image is 512 times 512. It's not very big image, so it won't take long. Just have to wait here. Here we go. So there are four matrices shown here. The first column showed the SSIM values, the second column showed the MSE values, and the third column showed the PSNR values. So each line, the first row shows the values for mean filter, the second median filter, and then Gaussian low pass, Wiener filter, BM30, and wavelength filter. So the same stuff happens when you do this. This is for Poisson noise, this is for salt and pepper noise, this is for speckle noise. And output here are all of the pictures that I output here. So let's see. For example, you have the image for Gaussian noise, for average filter, BM30 filter. So I'm going to show them on the presentation. Let's get back again. So here are the pictures with noise added. The first is Gaussian, Poisson, salt and pepper, speckle. So actually we can see the difference from eyes. Let's see, like the salt and pepper, we have bright noises on the dark background, and the dark noises on bright background. And Poisson is quite clean and not pretty much noises here. In Gaussian, the distribution is different. Some places are lighter, some places are intenser. In the speckle noise, it's just a uniform distribution, the noise over the image. So here's the result. So the Gaussian noise. So this is the original grayscale image, and here's the result of the images after the denoising technique. So first that's mean filter, median filter, Gaussian low pass filter, and Wiener filter, BM3D filter, and wavelet filter. So just from detected from noise, it's pretty much the BM3D filter has the best performance, and also we noticed that the SSIM value has the biggest value, which proves that this is the best one, because from the definition of the SSIM, when the value is close to 1, it means the better this picture is. So this the same for the Poisson noise, mean filter, median filter, Gaussian low pass filter, Wiener filter, BM3D, and wavelet. So still seems that, let's get back, still pretty much the BM30 filter is the best one, and it has the biggest SSIM value, which is 0.88. And salt and pepper noise, median looks good, Gaussian Wiener looks bad, BM3D wavelet is bad. BM3D is good, but there are still noises like here and here, and this is a SSIM 0.67. Let's go back, and the median has a 0.91, and actually the picture looks perfect here. So median one is the best one for the salt and pepper noise. And the last is the speckle noise. So you can see the mean. There is not so much noises here, but it looks a little blurry. And next is median, a lot of noise. Gaussian low pass, Wiener, and BM3D and wavelet. The BM3D here, it looks good, but there are still noises here, and the pictures looks blurry, and the SSIM value is 0.6642. Go back where to check 0.63, and mean value has a 0.69, which is the biggest one here, and it is the best quality, although it's still a little blurry, and but it deals with the noise very good, and there are not so many noises here. So summary, the image with the biggest SSIM value has the best noisy result. So this is detected from both the definition of the SSIM, and also we can prove it by just eye inspection. And next is BM3D is very stable and a comprehensive filter. It is a very good filter for all four types of noises here, and it's best for two types of noises, and it's still best of top 2 or top 3 noise, the noise filter for other 2 noises. And medium filter is especially good for salt and pepper noise, where I proved that it's almost the perfect one and eliminate all of the noises, it seems that. And final is that there's no perfect denoising technique among this, because the best one is changing, and I hope there is a perfect denoising technique that is universal for all types of noises. And the quality judging method needs further research, because we just detect them by using the SSIM values. So maybe there are other parameters that can detect the quality better than the SSIM. We haven't detected that. So that's the whole stuff of this presentation. Thank you.